Good morning. Today we'll discuss the property of the Z transform. Before that, we'll discuss one example, the Z transforms and discrete time Fourier transform. So, determine the Z transform of the signal. Of the signal. Signal is given x of n is equal to, this is 1 for n is equal to -1, and x of n is 2 for n is equal to 0, and x of n is -1 for n is equal to 1, and this is 1 for n is equal to 2, and this is 0 otherwise. Okay, so use the Z transform to find the discrete time Fourier transform of x of n by using the Z transform. Find the discrete time Fourier transform of x of n. Okay, so we have given, therefore we have to substitute these values in the equation of the x of n, so that we will get the solution. Solution for this is, so we have to use this equation, x of z is equal to summation n equal to -infinity to infinity x of n into z raised to power -n. So we have to use this equation and we can find the discrete time Fourier transform of the given function. So we know that the x of z for the given function, when you put here n is equal to -1. So when is equal to -1, what is the x of n? X of n is 1. Therefore, this 1 into z raised to power -1. So what will we will get? We will get z raised to power -1. So x of n value is -1. So this minus will be plus. Okay. Plus when n is equal to, second value is when n is equal to 2. So see, when n is equal to 1, the n is equal to -1. When x of n is equal to 2, n is equal to, we have to put 0. So when you put n is equal to 0, the value is 2. Therefore, n is equal to 0. So x of 0, what is the value? X of 0 value is 2. Therefore, it is 2. Now we have to substitute x is equal to next value, n is equal to 1. So x of 1 is value is -1. So we have to put n is equal to 1 is -1. So minus into z raised to power -1. this value is for n is equal to net is 1. Therefore, this is z raised to power minus 1 minus z raised to power minus 1. So when n is equal to 1, x of n is minus 1 minus 1 into minus n is equal to 1. So it is minus z raised to power minus 1 plus, now next is n is equal to 2. When n is equal to 2, what is x of n? It is 1. So we'll put n is equal to 2, x of n is 1. So this is 1 into z raised to power, and then n is equal to 2 here. So z raised to power minus 2. So this is the z transform of the given function. Therefore, we can obtain the discrete time Fourier transform of above equation can be obtained by substituting z is equal to e raised to power minus j omega. Okay, so we'll put these values in the above equation. Therefore, x of e raised to power j omega is equal to z raised to e raised to power j omega plus 2 minus z raised to power minus 1. So minus e raised to power minus j omega plus e raised to power minus j 2 omega. So this is the discrete time Fourier transform of the given function. Okay. Now next is the properties of the Z transform. Properties of Z transform. So most of the properties of the Z transform are analogous, or we can say it is similar to those of the discrete time Fourier transform, and therefore we can assume that x of n, its Z transform is x of z. With ROC suppose this is R1 and x of second is, suppose y of n is, actually this is small letters, so the z transform will be y of z with ROC, suppose R2. This ROC is R2. So ROC is changed by certain operations. So region of conversion is changed by the certain operations, and the general form of the ROC is a ring in the Z plane. We already discussed the general form of ROC is a ring in Z plane, and therefore the effect of operation on ROC is described by the change in the radii of the ROC boundaries. So first we'll discuss the linearity property. Linearity. In linearity property states that the Z transform of sum of the signal is just the sum of the individual Z transforms. Okay. The linearity property states that the Z transform of a sum of signals is just the sum of the individual Z transform. Is just sum of the individuals Z transform. And therefore we can write here A into x of n plus b into y of n. Its Z transform is the Z transform of the sum of the signals. It's just the sum of the individual Z transform. So it is S into x of Z plus b into y of Z. And therefore with ROC, that is R1 is intersection R1 with ROC at least R1 is intersection of R2. Okay, so ROC is the intersection of the individual ROCs because the Z transform of the sum is valued whenever both x of Z and y of Z converge. When both x of Z and y of Z converge, and ROC can be larger than the intersection if one or more terms in x of n or y of n cancel each other in the sum. So ROC can be larger than the intersection if one or more terms in x of n and y of n cancel each other. So therefore in Z plane this corresponds to the zero cancelling the pole. If the zero is cancelling the pole, that define the ROC boundaries. And this phenomena we'll consider in the next example. Pole zero cancellation. So let us consider the example. Here, suppose x of n is given half raised to power n into u of n minus 3/2 raised to power n. This is u of minus n minus 1, and this the Z transform of this is given x of Z is equal to minus Z over Z minus half into Z minus 3/2. And it's with ROC it is given. With ROC is given the magnitude of Z is less than 3/2, but it is greater than half. So this function is given to you, and output function is also given. and output function is given y of n is equal to 1 by 4 raised to power n u of n minus half raised to power n into u of n. The z transform of this is y of z is equal to minus 1 by 4 z divided by z minus 1 by 4 into z minus half, and with ROC that the magnitude of z should be greater than half. So this is the examples we have, it is given, and we have to evaluate the z transform. Evaluate z transform of a into x of n plus b into y of n. Okay. So the pole plot of ROCs for x of n, y of n, we can first show the pole zero plot. The solution for this is the pole zero plot and ROCs for x of n and y of n. So pole zero plot for the first function. So it is a half is greater than half but less than 3 by 2. These two poles are there but less than 3 by 2. So this is the first circle of radius half. This is another circle of radius 3 by 2. Okay. So this is 0. So the ROC is okay. So second function is having the poles at 1 by 4, and second pole is so here ROC is greater than half. Real part of Z, imaginary part of Z, and the C is the ROC and pole zero plot for So this is the 1/4 and maximum is here 3/2. So from the given function we can draw the z plane like this. Okay, so this is a real part of z, imaginary part of z, and therefore this is your ROCs. This is a z plane. This value is 1/4 and this is 3/2. Okay, so the linearity property which is we have just discussed, we can write we have to just add the sum of the individual z transforms. So a into x of n plus b into y of n, its z transform is a into minus z over z minus half into z minus 3/2 minus plus b into y of n. So y of n z transform is minus 1/4 z into z minus 1/4 into z minus half. Okay, so this is the sum of the individual z transform. So in general, the ROC is the intersection of the individual ROCs. So magnitude of z is greater than half but less than 3/2. With ROC, magnitude of z is that should be greater than half but less than 3/2. Greater than half but less than 3/2. So in this example, we'll see what happens when a is equal to b. When a is equal to b, suppose, then when a is equal to b, then what will be its addition? So a into x of n plus a into y of n. So this will be here a into minus 3/4 raised to power n into u of minus n minus 1 plus 1/4 raised to power n into u of n. Okay, so if you multiplied both by the n factors, so we see that the half raised to power n into u of n has been cancelled in the time domain segment. Okay, then ROC is easily verified now. Half into half raised to power n into u of n is cancelled in time domain, and therefore ROC is now the magnitude of z which is greater than 1/4 but less than 3/2. It is greater than 1/4 but less than 3/2, and therefore ROC is larger than the intersection of individual ROC. ROC is greater than the you can see. So this is ROC of the first x of n, and this is ROC of the second function, and this is the ROC of the addition of the signal. So we can say ROC is larger than the intersection of the individual ROC, because the term half raised to power n un is no longer present. Okay, therefore combining the Z transform and using the linearity property, that will give you combining Z transform and using linearity property, that will give you a into x of z plus a into y of z, and this equal to a into the Z transform of the x of z, that is minus z over z minus half into z minus 3/2 plus minus 1/4 z over z minus 1/4 into z minus half. Okay, so next, if you solve this further, a into minus 1/4 into z into z raised to power z minus 3/2 into minus z minus 1/4. This is after simplification. So z minus 1/4, z minus half, and z minus 3/2. And again, if you solve this further, we will get a into minus 5/4 z into z minus half, z minus 1/4 z minus half, z minus 3/2. Okay, so the 0 is at z is equal to half. 0 at z is equal to half. This will cancel the pole at z is equal to half. Pole at z is equal to half. Therefore, what will remain there after cancellation? So a into x of z plus a into y of z is equal to a into minus 5/4 z divided by z minus 1/4 into z minus 3/2, and hence the cancellation of cancellation of the half n into e raised to power n terms in the time domain correspond to the cancellation corresponds to the cancellation of the pole at z is equal to half by a 0 in the z domain. Okay, so this pole defines the ROC boundaries. So the ROC enlarges when the pole is removed. ROC enlarges when the pole is removed. Okay, this is the linearity property. Next is the time reversal. Time reversal property. So this can be denoted by x of minus n. The z transform of this is x of 1 over z with ROC for this is R1. Therefore, the time reversal, or we can say reflection, correspond to replacing z by z raised to power minus 1. Time reversal corresponds to replacing z by z raised to power minus 1, and hence if R1 is the form if R1 is of the form that magnitude of z is greater than A but less than B, then ROC of the reflected signal is of the reversal or reflected signal ROC of the reflected signal is the 1 over the magnitude of z is greater than A but should be less than B, or 1 by B is less than the magnitude of z and which is less than 1 over E. So this is the time reversal property. Okay, I think this much is sufficient. Tomorrow we'll discuss the time shift and the multiplication property.